Hello, BC Calculus students. This is Mr. Johnson, and these are the practice problems for section 8.1. And we're working on pages 11 and 12 for these practice problems. So we're going to look at, the numbers are a little bit strange here. So we're going to look at number 1, 2, and 5, and 6. If you're kind of feeling like you are starting to understand the process, you can certainly pause this and try these and then use this video to check your work. Or maybe it makes sense to work on a couple as you watch me and listen to me do it, and then you can pause and try the other ones on your own. But really, you do need to get to the point where you're able to start a problem and finish a problem on your own. And it really just takes a lot of practice. This is brand new material. You haven't seen stuff like this before. So you really need to dig into it. Every problem is a little bit different. And the more you can practice, the better. But you want to make sure that you're not just watching someone else do it. Whether it's your teacher, your friend, whatever the case is, you got to try to dig into these problems on your own as well. Okay, so for number 1, we're looking at a geometric sequence. And remember, a geometric sequence takes on the form of r to the n. And so right now it doesn't quite look like it's geometric, but if you were to do a simple rewrite, you have e divided by 3 to the power of n, and therefore r is equal to e over 3. And we know that e is less than 3, so r is in between -1 and 1 in this case, and since it's between -1 and 1, it is going to be convergent to 0. So our goal here with these problems is to figure out, is it convergent or divergent? If it's convergent, we need to specify what it's convergent to. So this particular sequence would converge to 0. Okay, with number 2, we have an alternator. Remember, we talked about that in the video. The -1 to the power of n is an alternator. So the first thing that I would think about doing here would be taking the limit as n goes to infinity and doing the absolute value so that I can basically eliminate the alternator and simply just take a look at the limit as n goes to infinity of the square root of n. Now, obviously, this limit is infinity. So what's happening with this particular function, or excuse me, sequence, is that it is going to alternate but continue to get larger in value. So it looks maybe like this. Let's say that maybe we have our first term here, and then our next term, and then our third term, and our fourth term, our fifth term, and sixth term, and so on. And what you can see is that it's the absolute value of each of the terms is getting larger, and yet it's alternating. So it's just getting further and further and further apart from each other like this. And we can see that it has to diverge then. Okay, let's take a look at, let's see, let's go ahead and write that. So this is going to be divergent. Number 2. Okay, number 5. This one's a little bit tricky because there is an alternator in there, but the problem is that the alternator is not multiplying the other portion of the sequence. So we're adding an alternator to the numerator, and then we're subtracting an n from the alternator in the denominator. One of the ways that I would think about this is to separate this out into, we've talked about the odd even thing. So let's say that we're looking at the limit as n goes to infinity, and let's say that n is odd. If n is odd, we're going to get -1 plus n over -1 minus n. So if n is odd, we get that. Okay, now, if that's the case, the -1 there on either side is going to be obsolete. We're going to get a limit of -1 here. If we were to take a look at the limit as n goes to infinity and n is even, that would make that alternator produce 1 plus n and 1 minus n. And that would be also -1. So no matter what, we're going to get a limit as n goes to infinity of -1. And so this particular one converges to -1. Again, keep in mind that that's a little bit outside the box, and that's part of the challenge with these problems, that each one is just a little bit different. You have to have a lot of tricks and techniques up your sleeve. Okay, here we have number 6, and with this one we have a natural log function in the numerator of this sequence, and we're going to take a look at this one and simplify it first. So this is e to the power of 4n divided by 3n. And using properties of logarithms, we can take the 4n to the front of the logarithm, and the natural log of e is just 1, and so we end up getting 4n over 3n, which is of course 4/3. So we've simplified down the entire sequence algebraically, and we get 4/3. So this is going to be convergent to 4/3. All right, let's go on to the next page. Okay, just 4 more here. And again, I suggest that you pause and try a couple of these on your own, and then you can check your work with the video and see how you did. This first one, we have an alternator again. And my tendency with alternators is to go ahead and take the limit of the absolute value of the sequence. And this alternator is different than in problem 5 that we did, where this alternator is multiplying the sequence. So this is a really nice technique, because then we can eliminate the alternator and just look at each of the terms in the positive sense. And this limit is 0. And if you remember, in this section, we had that theorem number 2 that said that if the limit of the absolute value of the sequence is 0, then the original sequence a sub n is convergent to 0. Okay, number 4, we have -1. However, the power 2n plus 1 is an odd generator. We talked about that in a couple videos ago, where we have these odd and even generators. That's an odd generator. So what that means is that no matter what n is, if n is 1, we get 3 if in the power. If n is 2, we get 5 in the power. If n is 3, and so on, we get all these odd numbers. So -1 to the odd power is always -1. So this is convergent to -1, because no matter what n is, you get -1. Let's move over to number 7. Number 7 and 8 are both sort of in the same ballpark in terms of the strategy and style. Now keep in mind that this is an alternator. However, taking the absolute value of this I don't think is very helpful, and the reason is that we have this trigonometry in the way. So with trigonometry, I think, not all the time of course, but I think it's the easiest to probably start listing terms. Certainly there'll be cases where listing terms doesn't make much sense with trigonometry, but I think often when you have sine or cosine in a problem, listing terms is probably the best course of action. You'll see a pattern often emerge, not always, but often. So let's say that n is equal to 0. So if we substitute in 0 into each of the n's, we end up getting cosine of pi over 2, which is 0. So our first term, if n is 0, is 0. Our second term, so if n is 1, we get -1. We then get cosine of pi, which is -1. So it's -1 times -1, so we end up getting 1 for our second term if n is 1. Not enough information necessarily. I mean, probably can determine that it's going to be divergent here just based on that immediate pattern, but let's just keep on going. So what if n is 2? So we would get an even power, so we would have a positive value here of 1. If n is 2, we have 3 pi over 2. That means that we would get 0. We'll just do a couple more here. That's if n is 3. If n is 4, we have the positive here. And now that oh, hold on, we got to back up. I wrote down, I hope I didn't say this incorrectly. I put a 3 here. That should be a 2. If n is 3, we have a -1, and then we have cosine of 4 pi over 2, which is cosine of 2 pi over 2. That's going to be 1. So this is -1 times 1, which is -1. And again, that's for n is 3. What we're going to find if we continue is that this pattern actually continues. As we apply more and more n values, we're going to get this pattern of 4 here. And so this is clearly divergent, and this is just by observation, which is a great technique to use, especially with trigonometry. Okay, here's number 8. So I'm going to do the same thing. If n is 0, I have sine of pi over 2, which is 1. If n is 1, we have a -1 times sine of, let's see, asking me 3 pi over 2, which is -1, so we get 1. If n is 2, So this was 0, this was 1. If n is 2, then we get positive 1 and then sine of 5 pi over 2, which gives us 1 again. And we will get 1 every single time, no matter what n is. And so this one, even though it's really ugly looking, converges to 1. All right, I hope that's helpful.